All right, so now our first lecture post-midterm on input modeling. So something we've been talking about, now we're starting to get into. Just a couple of announcements. So, you just had the first midterm A, or the pre-take is a term I kind of affectionately give the midterm in this two midterm setup. For those that are interested, I can show you the stats for that first midterm. Here they are right here. So the average score was 80%. The high score was a 97. That corresponds to missing one. So that's 36 out of 37. There were several students that got the 36 out of 37, but the one that those students missed were different. So a lot of times when I see that, I think, oh no, maybe I've made a mistake, and I go back, but those are kind of distributed around. I did make a couple of minor typos, and I went through and when there was a, or not just typos, but in the fill in the blanks, there were a few students that came up with alternate spellings or phrasings than what I was expecting. And so I went back in and regraded those to make sure that everybody who deserved points got the points. So make sure to review your results. And if there is a question that you think that was not automatically graded correctly, then just let me know. Just like on an ICA, if I try to anticipate all the different ways you can spell, uniformly or something like that. And so sometimes I don't make a great guess. So just let me know if you notice something there. Otherwise, so 80% average, low of about 41, high of 97. And, and the average time it took people, so we gave you 90 minutes, but it took everybody on average about an hour. So that's the stats on that, and I can leave those up here just in case you want to chew on that to make decisions about whether you would like to take the retake. So the retake is a week from today. So what's going to happen is Tuesday, we normally would not have class because of fall break, but there is no fall break this semester. So what I'm going to do is, instead of changing the whole lecture schedule around, I'm still going to be available Tuesday. I will still hold a lecture Tuesday, but there will not be an attendance question. It'll be an optional lecture, and it'll basically be like a midterm retake review session. I'll get to your question in the chat in a second. Thanks for that. So then on Tuesday, if you're interested in having an additional review session or to ask questions that have come up after the first midterm, that's fine. If nobody has any questions, but people show up because they're interested in that other review section, I'll bring along the same review slides that I had for the first midterm review, and I can see if those inspire any questions. And if we want to end early, we can end early too. So we'll just have an optional kind of midterm retake review day on Tuesday. You can come if you'd like. You can totally skip it if you want. I will record it and post it online just like a normal lecture, but it's kind of a bonus lecture. There was a question in the chat. Do you have to use Lockdown Browser to see the questions you missed? It is my impression that you should not have to do that. If you're having trouble seeing the questions you've missed, just let me know and I will change the access. Sometimes I don't get quite the same view that you do, and but it is my impression that you should be able to see the questions you missed at this time. You also can see the solution set. So I made a kind of a paper-based solution set, and all that's into the midterm module. So you should be able to see your score, the questions you've missed, and the solution set, which has some minor explanations. And if you have any trouble understanding why you missed one or the other, then let me or the TA know. All right, so there's another point in the chat that people are having trouble seeing the ones that you missed. I will take a look at that and see what I can do to make those available. And so actually, maybe if I can do this quick enough, in a portion of the screen that you cannot see, let me see if I can make an edit to that and see if, right now it says let students see the correct answer and let students see their responses starting on October 7th at 12 a.m. So at the moment it says you should. If you're not able to, then I will go ahead and go into student view and see if I can debug things so that I can eventually get those answers to you. All right, any other questions about the midterm or the midterm retake? Again, your score for the midterm will be the highest of those two. If you, decided you didn't want to take one, the 0 just gets ignored. So it's not the average or anything like that. If you don't want to take the retake, you don't have to. Likewise, if for some reason you didn't take the midterm and you just want to put everything into the retake, that's fine too. So any questions about stuff going forward? Pretty clear what we're doing on Tuesday. The retake will be on Thursday, and it'll be exactly the same setup as what we did on Tuesday, except a different test. So it'll be the same number of questions. I designed every question side by side. So I tried to make a question kind of as matched as possible in difficulty. The content is similar, but they're not, it's not, if question A was about resources, then question B might be about, entities or whatever. But to me, they're both kind of in the same kind of realm of material. So so it'll be a very, very similar midterm, but every question is totally different than the first questions. All right, great. Maybe I'll keep that over here for now. All right, so moving ahead, schedule. So there is Lab 7 was formally assigned this week. Yesterday I've gotten some questions about Lab 7 as people are getting used to Arena, figuring out where things are. It would normally be due Sunday, but again, due to the fall break, what I usually do is give you an extra week, and that's what I'm going to do this semester as well. So Lab 7, which was technically assigned yesterday, is not due this Sunday, it's due the Sunday after that. And there's no new lab next week. So, you could just totally ignore Lab 7 this week and pretend that it was assigned next week. That's fine too. So next week is, the original fall break week. So it's not actually fall break, but it's what would normally be fall break. The week after that, we'll do Lab 8, and so that's going to be online as usual. And this is a lab where I give you input data, because we're going to talk about input modeling starting today. And I'm going to give you input data for a number of different scenarios, and then you have to do some input modeling for that input data. So this is meant to be not only practice doing input modeling, but preparation for your final project. Because in your final project, we may be a little more flexible this semester, but in your final project, you have to go out and get data on a real system that you want to model, and then fit that data to, or fit models to that data to go into your simulations. And so this is meant to be a way to sort of sample how that would be done. And then after Lab 8, we will have, there'll be no formal lab, but there'll be kind of an open lab that allows you time to work with your final project team. And then the next 2 weeks, there's normal labs 9 and 10, where we cover some slightly more advanced Arena topics. And then the last 2 Wednesdays of the semester before the last week of the semester are other open labs that, again, if we were in person, then it would just be sort of like everybody would come to lab, and who would need sort of extra help. Things are a little weirder now with these kind of remote stuff, but that's kind of the timing of these things. So that's why we only have these 10 labs. There's a question that may already been discussed. Are my assigning teams? Okay, I'm going to get to that in just a second here. So final projects. The final projects have been posted, so you can look to Canvas for details. There's a general description, there's a description about a specific description about the report that we do, a 4-page report, and there'll be information about the presentations. So the basic idea of the final project is you analyze a real-world system using Arena. For those of you who entered the formal competitions that are sponsored by IISE, you kind of follow their lead on what that system is going to be. Otherwise, you would choose your own system. So I want to model a coffee shop. I want to model my my family's guitar making business. These are all examples people have done in the past. So there's, and then if you sort of want the kind of more examples, if you go to your textbook in chapter 9, exercises 1 through 5 have some examples of the types of things, like they say, like go out to this thing and take data on this particular aspect. So those are maybe some nice examples. So things like small grocery stores, cafeterias, traffic intersections, laundromats. These are kind of common ones. And then, normally in the before times, there would be a lot of interesting operations questions around ASU's campus. So about walk-only zones and other coffee shops and food services and classrooms. Now ASU is a bit of a ghost town, so it's a little harder to gather data there. So this year or this semester, because of the weirdness of things, I'm also open for you to getting creative about maybe not gathering your own data, but finding data sets online. Or, and I think I posted some of the resources on this on Canvas, but there are webcam repositories that are just focused on particular cities, 24/7. And you can say, all right, I can't, maybe I don't want to go out and take data at this particular intersection because I don't want to put myself at risk, or however you think. If you can get access to, all right, well then it's not ideal because I'm locked into this view, but maybe I can actually see how many people go in and out of this Starbucks in New York City, or something like that. So we can be creative about where you get your data sets, or if worst comes to very worst, you can do the things that actually you're going to do a lot in real life, where you'll come up with input models that have a right structure, and you'll make arguments for the parameters you've chosen based on something that may not be raw data. So it might be a sort of a back of the envelope calculation where you say, well, I need to know the average number of people who arrive at this particular location. I know it's probably no more than this, but it's probably no less than that. So I'm going to say it's about this much. And I ran my model with a number of different values around that range, and I didn't get any different results. So I'm assuming that it's relatively insensitive for normal ranges. So these are things that in the past, I would have really wanted you to have raw data, but I don't feel comfortable asking you to go out and getting raw data if you're not comfortable with doing that. So we can be a little more flexible this time. Now, this is a group project, and so the normal guideline is I want you to have 4 team members, and I would normally have a minimal number of 3-person team members. But I have gradually been shifting how I do this final project, and this kind of like this COVID times has kind of like been my push to kind of totally virtualize the project, where your presentations for this project will not be in person, obviously, but and so because of that, we don't have to worry about fitting everyone into a fit number of presentation slots. And so because of that, I'm okay with having a few more teams than normal. So, and I also know that's going to be hard for some of you to find, a whole bunch of team members. Of course, I want you to post to the discussion boards, and I will try to provide Google Sheets, sign-up sheets and things like that to help connect you guys together. But I know that some of you aren't, even in Tempe, and so it's going to be hard for you to find each other. So I can be very flexible on the group size here. And if worst comes to very worst, if you really want extremely smaller size groups, then we can talk about that. But shoot for 4. If you can find 3, that's great, and then otherwise we can talk about any other changes to that. I'm not going to assign your teams. I want you to sort of find those. But of course, when we get to the point where there's a group formation assignment, which is coming up that I'll talk about in about 2 weeks, then if there are people that have had a hard time finding each other and let me know that ahead of time, then I will try to match up those who have reached out to me and said, I can't find anybody, and then I can sort of match you guys up. And what's nice about that is because we all know how to participate remotely now, then even if you're in different locations, there may still be ways, as long as your time zones aren't too far apart, that it'll still work out. So that's kind of some basic info about the final project. In about 2 weeks, like I said, you'll need to sort of submit who's on your team. And that's sort of 1% of your final grade is just this tiny little Canvas submission where you submit, 4 names or 3 names. And then about a month from now, you'll submit what's called an input modeling report. And this kind of serves as a proposal for what you're planning on doing. And it would normally also show me that you've gone out and taken some data or have at least some ability to parameterize input models. So it helps me to see that you've identified what input models you might need for your simulation project, and that you're able to get data to help you parameterize those input models. And then the last week of classes, in the middle of the week, that's when, and if you can hear whining, it's my dog is wanting attention, so I apologize for that. My wife is away for about another half hour. And so the oral presentations here, midweek, the last week of classes, and I'll tell you why midweek here in a second. They're pre-recorded, so you basically upload a 10-minute video that is your presentation. And that same day, you also submit your final report. And I'll tell you why in a second, why it's midweek like this. And then, I guess, okay, I can show the dog. I will do that. That's fine. So this is Fritz. Fritz, you're going to be on camera. So I'll hold you up here for a second. So yeah, so then at the end of that week, we've got peer reviews. And so the idea behind these peer reviews is that everyone is going to be randomly assigned a single oral presentation and a single report. And that random assignment is, so every individual student is going to be assigned another group's report and then another group's presentation. And it might just be that that same group, you might happen to get the same group, but most likely you're going to get two different groups. And then I give you a rubric. And so then you then fill out that rubric and give that other group a numerical score. And then you also give them some constructive comments, like, you know, you know, what you liked and what you disliked, maybe just a couple of sentences. And then that gets submitted to that team anonymously. So they won't know who you are, but you of course are going to know who they are from, you know, the names on the report and everything. And then I will look at all of the presentation grades, and I will look at all of the presentation comments, and then I will give the evaluators a credit for doing the peer reviews if they gave, you know, constructive comments. And hand and Fritz off. And then I will then come up with scores for your own final project reports and presentations based in part on the peer reviews and in part on my reflections of your report. And so it is a way that you hopefully can sort of not only learn the importance of some of these aspects of technical communication by writing a report, but also by reading someone else's report and sort of seeing like what works and what doesn't work. And so that's why I think it's important to this peer review process. So that's kind of how we're going to arrange that. And that is why I make these two things due in the middle of the week. I know it's kind of a drag, but that gives you enough time to do the peer reviews by the end of the week. Now, sadly, they've done this innovation quarter thing, which knocks out our normal finals week, which means that the final exam, you know, is also going to be that week. But we originally were going to have a pre-take on Thursday, and a little bit later I'll tell you what I'm going to do about the retake, which can't happen when it normally would happen, which would be in final exam week. I'm going to do something a little bit different that allows for something retake-like, but also allows for us not to take up that time during the final exam week that we're not allowed to give you exams in this semester. Okay, so any questions about these deliverables here? I've got some other details here, but I mean, these are details like, you know, 4-page report. We'll go over all this later, but basically 10-minute presentations, a 4-page report, maximum length, and then again, the grades are determined in part from peer reviews and in part from my evaluations. So start soon. The biggest thing is to start thinking about who you want on your team so that you can assign that names of team member assignment, which I think is already available for you to fill out if you already have a team in mind. Okay, yeah, so any questions about the final project? Is there some sort of Discord or other chat room where you can reach out to others, the students without a team? Thanks for mentioning that. There is a Slack page that has been built for this class. If you go to Canvas and you look down on the left-hand side, you'll find Slack workspace, and everyone has access to that. Occasionally some questions about the homeworks and things have been posted there, and I've tried to monitor that. And I could create a channel or something like that, or you could just use the general channel. So feel free to use the Slack workspace, feel free to use discussions. And then what sometimes I like to do is create like a Google spreadsheet where it'll basically have like, these are people looking for a team member, these are team members looking for a group, and it sort of helps with matchmaking. So I can also do that in maybe the next week or so, is to organize that and post it on Canvas. So great. Any other questions? All right, final project is just a standard. I know people think, I hate group projects and term projects and all that. And you know, it's a simulation course. It's a standard aspect of simulation. It's kind of something that we have to have here. And the group, you know, team working is also something that ABET wants us to have you do. So It's just part of the standard thing. Any sim course you're going to take at any school in IE, it's going to have you do a group project, you know, for stochastic sim. Canvas activities, there is a new Canvas activity available, or I guess it's already been available. It's due before G3, which is, you know, due in quite some time. So you got quite a while here if you consider the retake and all that. There is a homework that is available. Technically, you can start it now if you want to read ahead. It's named G3 because you're not technically like have the content available for it until after lecture G3. So you've got quite a while. So it's due 2 weeks after G3. So today's G1, and then we've got a retake, and there's this fall break thing. So there's quite a while to do this homework. Then after that, there's homework J2, and that's the last homework. So there only are 2 other homeworks in this class, and there's not that many ICAs left over either. So really, we're getting to the point of the class where the grade shifts from these small scale assignments to your final project. So again, think about your final projects. All right, any other questions before we move on to new stuff? Again, for those who came in late, if you're interested, here are the stats on the midterm, the first midterm. If you figure out where you land in this distribution and where, you know, how that determines whether you're interested in taking this retake, which is a week from today. Thanks for your patience with the dog. All right, great. And let me make sure no questions have popped up. All right, good. Okay, so moving on. So moving on, we have been working on random-variate generation. As you all know, you're all experts in this inverse transform technique, where you take a nice rectangular shaped uniform distribution and you push it in to the mold, which takes the form of the inverse CDF, and out of the mold comes, so it's almost like, you know, it's like an injection mold, and it's like the reverse image. It's almost like the inverse CDF is like the reverse image of what you want. And so you push this thing into it, and what out pops, you know, after things cool and everything, is something that's shaped like what you actually want. So you're sculpting the uniform to look like what you actually want. So in this case, we've got the CDF of an exponential. So it's this nice rising, you know, decaying exponential shape. And you push things through the inverse and you get the nice exponential coming out of it. So, you know, this is kind of an example similar to what was on the midterm. You know, I give you a PDF, a density function like this one, and I hope the examples that I tried to give you on that first midterm, you could manually solve by hand, but the kind of trick behind them is that there were shortcuts if you just thought about the geometry of it. So like in this particular one, I can see that if I'm just integrating under this curve from -infinity to x, then for any x that's less than 1, it's just the area of this triangle that's over here. So again, I can go through all the math, but if you think about this 1/2 x squared that's here, that 1/2 x squared is just 1/2 base times height, because the base is going to be x long and the height is going to be this high, and the area of a triangle is 1/2 base times height. And so that's all we're seeing here is the area of a triangle. So whatever that x is from 0 to 1, then it's just 1/2 x squared. That ends up being the CDF for this first part. And if I want to invert that, I just set R equal to that. I do some solutions. These are all positive values. And so I'm going to choose the positive here and I end up getting an inverse transform. I end up getting a random-variate generator that looks like this one here. Now for the other parts of it, I think, okay, so this is again where the geometry really, really helps. So even without doing any integration, if I look at this, then I see if I want to integrate under this curve from -infinity to this x, where x is between 1 and 1.5, that area is always going to be this constant triangle area plus this rectangle, where the rectangle's width depends on x. And so if I look at this triangle's area, well, that's just 1/2 base times height. The height is 1 and the base is 1. So the area of this purplish color is 1/2, which is what we have down here, 1/2. And then the area of this rectangle, well, the height of this rectangle is 1. And the width of this rectangle is x minus 1, because there's the x value here, but I only care about this width, x minus 1. So if you go through all of the integration, if you've done everything right, then what you get is just 1/2 plus x minus 1, which simplifies to x minus 1/2. And so that ends up being my CDF there. So I could have got this CDF just by looking at the geometry of this problem without actually having to worry about the integration. And if you go back and look at midterm A, that one I've given you, that's actually how I did, I think, the solution for midterm A when I was writing it, is I just thought it out in terms of the geometry. And then I think I might have wrote a couple of integrals in my solution set, but you know, the quick way to get to it was just through the geometry. And then I can invert that single piece, and I can plug in these x bounds. And if I plug in these x bounds into the CDF, it gives me the r bounds down here. And so that's an example of how to do that. And then so I can implement that in Excel by taking those formulas. So here's these formulas up here. I can turn that into an if statement and say, if my random variable, which I've drawn in a previous cell, is less than 0.5, I use the top formula. If it's greater than or equal than 0.5, then I use the bottom formula. And I could do 1,000 rows of that. And then I could do a histogram. And so all the stuff for histograms. So I'm just kind of going over this, just review, and you end up getting a histogram that looks like this one. So your previous homework D2, you all did this. So hopefully this becomes, you know, as comfortable. And then if we look at that, that looks just like we were expecting. So the original shape was a ramp that went up to 1, and then it was flat after that. So it matches what we were expecting. So that's good. If I didn't want to do it in Excel, here is exactly how I would do it in MATLAB. I can draw 1,000 random numbers, and I can then find all of the random numbers I drew that are less than 0.5 and plug them into one formula, all the random numbers that are greater than 0.5 and plug them into the other formula, combine all those things together, and again, get a similar histogram. So I can do that in MATLAB as well. Then I can also, of course, do this in Arena. So I built a little block here where I create entities. The entities go through this assign block that assigns them an attribute called trap delay, their trapezoidal delay, and then they're delayed by that trapezoidal delay and then disposed of. And in this assign block, I assign a random variable R, this RA, that's Arena's way of saying a uniform random variable between 0 and 1. And then I implemented the same formula I did in both MATLAB and Excel, assigned it to an attribute called trap delay that rides along with that entity, and then delays them by trap delay. And so there are ways to use histograms inside Arena as well. And so there's some real-time visualization. If you look at the text surrounding the exercise for Lab 7, you'll find out about all the cool different plots that you can put in right on top of an Arena plot, like for the inventory management and such. And then you get a histogram, which again, it looks like the nice trapezoidal shape. So I could go through that, I'm not going to, but if you'd like to have another example you can practice on, here's the trapezoid flipped the other way, and it's gonna have, you know, you can do the same geometry, you can do all the same stuff, and you get the same sort of things out. So I've got a trapezoid that looks like this one. This is what I was expecting. And I do a histogram of my inverse transform generator, and it looks exactly like I was expecting. That's great. So, but how do I rigorously compare them? How do I really say that this data set up here most likely came from this probability density function or this random variable? How do I really know that? How can I say that rigorously? Now, we've already answered that question for a specific distribution, the uniform distribution. We already know that if we get a bunch of numbers that come out of a pseudo-random number generator, we can rigorously test whether they came from a uniform distribution. We have tests for that. We have the chi-squared test and we have the KS test. And so if we want to then figure out all about other distributions, we just need to find a way to modify our KS test and our chi-squared test to test for other distributions. And yeah, so sorry, I mentioned that a hypothesis test. That's right. So the hypothesis pre-midterm was these came from a uniform distribution. And now what we're going to find out in this unit is how do we change that hypothesis to be other distributions? So we're going to say, if my hypothetical distribution is this trapezoidal distribution, how do I test the hypothesis that these data came from that trapezoidal distribution using the same tools you've already learned? So we're going to make a modification to the chi-squared test and the KS test to allow you to test other hypotheses, not just uniformity. That's what's coming up. But then the other thing that's coming up in this unit is, how do we pick these things to begin with? How do we know that we should even pick a trapezoid? You know, where did that PDF come from to begin with? And I've already given you some hints as to, well, you know, if it's this type of process, it's usually this type of random variable. And we're going to drill down deeper into that in this section. All right, so that's all review stuff. And so I just want to make sure, you know, everybody feels comfortable with that content. Are there any questions about the inverse transform stuff or anything like that? Or do we all feel pretty confident with all of this so we can move forward onto this new input modeling? We're going to be drilling down deeper into choosing distributions and parameterizing them. All right. And by the way, I'll take this time to mention that Swastik Nandan, our instructional assistant, has come to the actual physical classroom right now. He is there. I am broadcasting there. And so now for all lectures moving forward, if you really are excited about attending in a classroom, that is available to you. So that is there. And if nobody shows up, he might not stick around for the whole time. But otherwise, if you just rather for some reason be in the classroom with this, as I said on Canvas, prefer, if you can, to bring a mobile device or a laptop, because it's just easier for me to participate with you if you're in Zoom. But if you don't have any of that, if you raise your hand or anything like that, Swastik will get my attention and you can still answer questions and, you know, and point a microphone your way and so on and so forth. So we can make that happen. Okay. All right, so let's do an attendance exercise. Yeah, let's wake everybody up a little bit. So attendance exercise URL is on the screen. It's also in the chat. And so my attendance exercise here is just as a reminder, tell me one of the two tests that we use for testing whether data come from a particular distribution. So I just mentioned that there are two tests we learned before the midterm that tested for uniformity, and we are going to modify them so they can test for other distributions. Choose your favorite of those two tests. So I'll put that in a question, is that what is one of the tests that we have learned to use to test data's fit to a hypothetical distribution, e.g. uniform? Okay. All right. So how do we build these input models? Well, here's our motivation. We got a really simple arena model like this. So you guys have started to draw these things. In Lab 7, you're going to be using these basic blocks to build a little inventory management system. I'm really excited about that. And so as you're building these things, then there's all sorts of activities. You know, there's durations, there's probabilities that need to be filled in. These are input models. And so if passengers arrive to an airport, well, at what time? You know, how do we model the time in between them? Passengers need to go and get their IDs checked. Well, how long does it take for each passenger to get their ID checked? How many of those passengers get flagged as their ID needs additional scanning or they get turned away? You know, these are all things that we model stochastically that we need to then come up with the right probabilistic model for. So if we focus just on passengers arriving, you know, I've used this example before. You know, we know that we're going to use this stochastic approach where we're just going to effectively, as if this was a you know, a board game or something like that, roll a many-sided die, and that many-sided die is going to then tell us what the distribution between these things are. It works for board games. It seems realistic enough, so hopefully it works for us as well. So we need to choose the die to best capture reality. So we would like, in the case of passengers arriving to an airport, perhaps for a distribution to, you know, we have data that we've taken that looks like this. So we've actually taken real data and it looks like this histogram here. And we would like to choose a distribution that, that fits this as well. And so we, might say, well, does an exponential fit this? And if not, what other things fit this? And how do we rank these distributions? And so if we end up choosing that exponential, then we can go in and go into ARENA, and we take that parameter that we've ended up fitting. So we might have said, we think an exponential is best. And so we are going to then find the best exponential parameter. Well, the mean here, the best fit parameter that fits this exponential to these data is a mean of 19.88. And so we take that parameter and we put it into ARENA. So we drill down into this block that creates the entities. We say we want an exponential inter-arrival time. We want to use this 19.88. And that 19.88 is going to come from our data. So in this unit, we're going to learn how to take data and turn them into these parameters that we put inside ARENA, so that ARENA can generate arrivals that look similar to the arrivals we see in real life. So we put that into our stochastic sim that we've built. We hit run, maybe run a couple of replications, and then we go into Crystal Reports, and Crystal Reports tells us that for every customer, you've got this waiting time, and this waiting time has a certain amount of variation. You have this many number of people waiting at a particular queue, and so this was the average, and it had some variation as well. So you get variation on the output that came from variation on the input. And so the only way we can trust the variation on the output is if we trust the variation on the input. And that's kind of what we're saying here. So modelers like to use the term garbage in, garbage out, or GIGO or GIGO. And so this idea is that no matter how beautiful your model is, you can put this block diagram up on a PowerPoint presentation and someone will say that is exactly what happens at an airport. You've captured every aspect that's important. We buy in, you got it, you have the structure just right. But all of these input models that go inside the create block, inside the process block, inside the decide block, those are the things which take your beautiful model and turn it into either an outcome that is useful or an outcome that is total garbage. And so it's the garbage that goes in that produces the garbage that comes out. Of course, you can get this wrong as well, but the kind of insidious thing here is that a really well done structural model here can be totally ruined by something that you can't even see on the diagram, and that's the choices you've made of these distributions coming into these pieces here. And you can think of this as like fashion models. You can have something that looks like a perfectly good jacket, but when you actually put it on, it looks terrible. And you say, why does it look so terrible on me? And it just so happens that that jacket was built for someone who maybe doesn't share all the same physical aspects of you. And so that's why the model that's almost like the model, the person that was put into the jacket, that's like the garbage going in here. So the jacket is like the structure here. And in order to evaluate that structure, you need to have the right stuff going into the jacket. And so you need kind of the right shaped model to sort of say, like, does this person actually capture the salient features of me? Okay. So just a cartoon that is sort of handling that as well. All right, so so our overview of what's going forward here. So input modeling, it selects probabilistic models that mimic these variations. Examples that you've probably seen in other classes. For queuing systems, we typically need input models for inter-arrival times and service times. Hopefully I've beaten you over the head with queuing examples that makes sense. For supply chain models, I haven't beaten you over the head with this so much, but in lab 7, you're going to see in that supply chain model, and just like in a muffin sim model, there is a demand model and a lead time model. So how many orders do you get per day? And how long does it take for your re-inventories to end up cutting back to your inventory? So that comes up there. And then reliability, we haven't really done many reliability problems outside of just mentioning one example in I think some of the first unit is failure time distributions. And so you've actually in a previous lab, you had to add failure times into a factory simulation. And so you had to say, all right, at particular times, then this machine is going to go down and the resource capacity is going to suddenly shrink. And so, well, how often does that happen? You've got to get the model for that right. And so these distributions model the real world. And so poor choices for these probabilities, the models or their distributions can lead to poor operational recommendations. And that's why input modeling is just so important. So the 4 steps was we walk through Unit G is today we're going to talk a little bit about collecting data from the real system. And you should think about this in terms of your final project if you're planning on collecting data, which I highly encourage you to if you're comfortable with that. Then identifying a probability distribution once you've collected that data, and then parameterizing that probability distribution. And then once you've done all of that, evaluating your final chosen distribution and saying, okay, great, I've chosen the best fit distribution, but even though it is the best fit distribution, how much variance is left over that I haven't explained? And that's kind of, so that'll be the back end of lecture G3. All right, so any questions about anything I mentioned so far? Is it pretty clear what I mean by input modeling? So I've already asked a question on the previous midterm about, what is input modeling? So I really want to make sure that people understand that input modeling is not about entities coming in so much as probabilistic models coming in. The models are the inputs. Does that make sense? I've had students ask me before, I don't know, about, I've ended up answering some questions about analogies to fountains, and it's like the water going into a fountain is just constantly being recycled, kind of like the entities in a model. But the flow rate of the fountain, how high the fountain, pushes the water, things like that, those are kind of like the real inputs to the fountain. The outputs to the fountain is how it looks. So the entities, don't think of them as inputs, think of them as just part of the model that's shuffling through the model and constantly being recycled. They go out one end and they come in the other end. But how they get modified as they move through the model, that's really what the real inputs are. Okay. Okay, all right. So today we talk about the pitfalls of collecting data. And so the one thing is you will see, at least if you, depending on how you do final project, you're gonna deal with these cases where you end up running into data that's not always relevant data. So let's talk about an example here, and we'll have some interaction opportunities here. So simulation study is going to investigate how to reduce time patients spend in a clinic. So the entities are patients, and the activities might include a nurse obtaining patient history. It takes the nurse a certain amount of time to obtain that patient history, and we want to model that amount of time. For some patients, it's shorter, some patients, it's longer. So we want to know what is the probability distribution that models how long it takes a nurse to take your medical history. Okay, so you look and you find data from a prior 2002 study. And that prior study collected timing data on nations taking patient history. Now, these data are still available. I don't know why I said this data, but these data are still available. And the question is, should the data be used? And so this is 2002 and is when the data are from, and it is currently 2020. Now, some of you may not have known what it was like to go to a clinic in 2002. Just as I have a certain model of the age distribution of what's in this class, and I'm sure some may have gone to a doctor and remember that, but some of you may not. So, but I think you could probably take some guesses. So, so why don't we do this? What the heck? Let's do a breakout room. We haven't done that for a while. So I'm going to do a brief breakout room. And I want you guys to discuss why these data might not be relevant currently today. So what might be the problem with using these data? So let's do, put on the all right, so here we go in the breakout rooms, just be a couple of minutes at most, and then I'll bring everybody back. All right, so bring everybody back. Let me make sure that we're all here. Looks like it. Okay, so I popped around several breakout rooms to discuss or hear what everybody was discussing. I heard some great things. So what are some, does anybody have anything they want to offer as some solutions to this question? And I will maybe reshare the screen here. And while I reshare, feel free to either speak up over the microphone or put your answer in the chat. And I already put a couple answers in the chat. And I will take a look in just a second once I reshare. Okay. All right, so I see some answers in the chat here. So like there may be new diseases or conditions that are now being tracked that were not in 2002. I had not thought of that. That's a really interesting point, is that there might be additional things on the questionnaire that we don't ask for. So right now, if you've gone into a clinic, they test you to see if you have a fever, you know, and so normally they wouldn't assume that you might have a fever, and unless you complained of symptoms of that. But now, you know, so there's other things they might do, other processes. I see another point here. Data from 2002 may not capture variation that happened in 2020, given healthcare systems that have changed. And I trying to figure out what, you know, healthcare systems, what we might mean by that, but I assume you might mean like technologies that might change. I know that back in, you know, if I went to a doctor visit in 2002, actually there was a lot of paper-based recording, or there might have been computer-based recording where they would roll in a computer, but now there's tablets, and you know, they have a totally different way of taking down data. And even if they were asking me the exact same questions, the process has been, you know, it might be sped up, it might be slowed down, but the whole point is that the machinery they're using is totally different. It's like a totally different factory or supply chain. What other things we have? Data may not even apply to current workspace conditions. Nurses may not even collect patient history anymore. It may be done in the waiting room. That's an excellent point too. So you may not go into a room and get your history done there. It might be done, you know, at a kiosk or ahead of time. You might have submitted it online, and you just give that to them, and then they read your forms before they call you in. So it's, again, a totally different process. The resources might be totally different due to new technology with different activity times. Exactly. These are all excellent reasons why, even if you're modeling the same process, and I see another, the data might be relevant if we're trying to evaluate a comparison to more current conditions. So that's an interesting point. If maybe we really do want to model what it was like in 2002 and what it was like in 2020, and we want to see, have things really improved? And we might want to simulate what would happen if you got a burst of traffic in 2002 versus a burst of traffic today. And you might want to say, are we really better off today? Well, before knowing if you're better off today, you need to be able to consider the hypothetical scenario of what would have happened in 2002. Well, in that case, you better get the 2002 one right. So depending on what question you're asking, then maybe these 2002 data are relevant. That's an excellent point. So thanks for bringing that up. So yeah, another point, sometimes you put information on ahead of time. So the nurse may not have to gather much info from you because it's already been taken care of ahead of time. So this is a reason why just because data are available doesn't mean that you actually should use them. So that's like the first step in data collection, is to resist the temptation to use data that's available. Dr. Montgomery, if some of you might know him, Doug Montgomery, he's sort of kind of famous in industrial engineering for being one of the big sole drivers behind design of experiments. DOE or DOX here at ASU is kind of about to retire. He has a bunch of great stories about him working in industry and about people providing him data sets instead of allowing him to do experiments, because experiments would cost money. And so they say, here's a data set. And what he would end up finding is that data set would sometimes not have variation in the thing they were asking him to study. So he might say like, oh, that, you know, like, that he found no effect of temperature on a particular adhesive property for floor tiles or something like that. And because all of the data sets showed that, you know, there was no statistically, if there were no changes in temperature led to changes in adhesion properties. And then he finds out later that all of the data that have been gathered were gathered under conditions where temperature was tightly controlled. So there was no variation in temperature. And so of course he didn't see an effective temperature, because temperature, you know, was stuck at the optimal level. If he would have ran his own experiments, then that temperature could have varied, and then they could have actually seen the difference in the output. So there's a bunch of times when people say, here's a data set, you really need to say, you know, I might need to run my own experiment. Summary statistics are not the whole story. So I'm sure some of you have seen this criticism before. It comes up in politics and things like that. So if I study people moving through a metal detector, then, you know, you might say, how long does it take to walk through a metal detector? And someone might say, okay, I take 1,000 observations of people walking through a metal detector, and I see that on average of the data, so these are data like taking from, okay, they started walking into the metal detector, and then I wait for them to finally exit the security setup, and or exit, you know, I see them actually moving away from the metal detector to pick up their things on the other side of the X-ray machine. And that average time after 1,000 observations is 30 seconds. And so you're like, all right, 30 seconds, I'll just put that in, done, 30 seconds. But then you need to really ask yourself, like, you have expert domain knowledge. Your mental model has a lot of useful stuff in it. And you need to say, does it take me 30 seconds to walk through a metal detector? I'm guessing most of you would say no. It probably takes me 2 or 3 seconds to walk through a metal detector. And yet the data say the average time to get through this metal detector is 30 seconds. And so that makes you think, let's look at the data more. And you might see that the distribution is actually bimodal. What do I mean by that? Is if I look at the distribution of times, so these here are the times it takes to walk through the metal detector, then I get maybe a distribution here that has if I were to just focus on this one, an average of 2 or 3 seconds. But then there's a second peak way out here that's at, say, 60 seconds. And so maybe this one is way out here at 60 seconds. And so now, even though this one is at my 2 or 3, then this one out here at 60, when I average all of the data under here, then I end up getting an average value. Remember, that's where you kind of balance these things if they were on a teeter-totter, of 30 seconds. And so that's actually right in between these two modes of the data. And so that tells me that there's something else going on here, and I need to properly model this bimodal distribution. So how the heck do I do that? And where is this coming from? So I make a revision, and I think about this bimodal distribution, and it makes me realize that maybe there are two things going on here. Some people are passing right through the metal detector, and the others are getting flagged, and they end up getting triggered, and those ones need additional screening. So it takes them a while to clear the metal detector because they're getting additional things going on that the other ones didn't go through. So we're actually seeing two populations of people. And we've got a model for the population that get right through, and a model for a population that need the extra ones that are being merged together. So we may need to then rewrite our ARENA model so that it properly models these additional variables so that we can get both of these populations. And so, so that's, you know, and this is, I'll show you a more concrete example of this next time, where we'll actually draw this out in ARENA, where we build these two populations, and we build another model for the probability of being in one of those two populations. So we have a model for arriving to the security area, and then a model for being one who doesn't get flagged or one that does get flagged. And if you don't get flagged, you get a short passage time. And if you do get flagged, you get a long passage time. So you got to be real careful of means and look at the shape of the whole distribution. The other thing you'll find when you look at your data is sometimes things show up like negative values for durations. A time duration should never be negative. But I'll guarantee that, you know, if those of you, let's say you're going to do a traffic intersection problem, and you're seeing, well, how long does somebody take to pass through a traffic intersection or wait or something like that. And occasionally you're going to find that some car calculates as a negative time. And this might just be that when you were taking the data, you entered the data in the wrong 2 columns. This happens, you know, you got, you know, 100 rows of data for 100 different cars you watched to go through the intersection, and you just flipped the enter time and the exit time around when you were entering these data in for one of the cars, and it comes up negative. That one little data point, if you took the average of all those times, you might not even notice that it's there. It will be pulling your average value, because averages are very, very sensitive to outliers. So that one negative value will pull your average one way or the other. It will totally affect your average, which so it's important to go through your data set and sanitize it and say, are there any values, are these outliers true outliers? Or does this indicate I did something wrong in my data collection? And then what do you do? So you could say, oh, it's a negative value, and it's clearly a negative value because I just flipped enter and exit time and I did the subtraction wrong. So I can just unflip those. But sometimes it's not quite clear what happened. And you say, well, maybe I can just discard the data. But you have to be careful, because as you discard the data, then you might end up biasing your distribution. So this censoring problem happens all the time with failure time distributions. You observe a classroom for a month and no light bulbs ever burn out. And so if you're trying to estimate how long it takes for a light bulb to burn out, then just based on that month-long data, you don't have the data that actually for the real failure times. So your best fit model is that, well, I guess they just never burn out. And that's because you effectively, if you observed for longer, if you had more data, you could actually get the right distribution. So you really have to be careful about, if you remove data from a data set, am I going to be reshaping the distribution so it's a biased data set? So so that's kind of the thing, that whenever you remove outliers, you need to ask, like, well, what happens to my distribution when I remove it, when I put it back in? You need to sort of test these hypothetical scenarios to see, is it safe to do this? All right, so basically, you know, the kind of, you know, what is the process that you'll go through here? So if you're starting your final project, for example, you're trying to think, what do I want to model in the real world? You come up with a candidate system. Before you even go into that input modeling report, where you say, these are definitely the things that I'm going to need. I need to monitor the inter-arrival times, the service times, or whatever. Just go and look at the system for a while and do some pre-observation. And you'll find out that there might be some aspects of the system that weren't in your mental model. And those aspects really do need to be modeled. So that's what we mean by pre-observation in planning. The other thing you can do, though this is dangerous if you do this inappropriately, is analyze your data while it's being collected. So as you're seeing the data come through, then is it showing you the variation that you were expecting? Are you getting negative values out where you're not expecting negative values? Are you starting to see that a distribution you expected to be nice and unimodal, that you could fit to one of the distributions that we've talked about pre-midterm, is coming out trimodal? And if it's coming out trimodal, then that might mean that there's actually 3 populations that you need to model independently. And you need to now model how those populations, you know, where do they come from? How do they get split up? So do I need to make fundamental changes to the structure of my model? I liken this to, I bought a jacket that has 2 arms. And then I end up finding out as I'm building the jacket that the population of people that I'm making it for, turns out they're aliens that have 4 arms. And so at that point, I need to sew in 2 more arms in my jacket. So that's something you kind of need to like call an audible or something like that, using a sports metaphor that says, you know, we notice that there's a problem that based on the data that we're gathering on the demographic we're trying to model, that these data aren't going to fit the fundamental assumptions we made in our model, and we need to change that model. Now, this is something that is probably going to happen to you, and this is a very common thing, is that you often have potential heterogeneity across your observational periods. You might go to a bank on Monday at noon and take data on customer arrivals and what they need and those sorts of things. And then you end up coming back on Tuesday, and you just happen to come back at 8 a.m. The types of customers that arrive to a bank at 8 a.m. on a Tuesday might be very different than the types of customers that arrive at a bank at Monday at noon. And so you need to ask yourself, can I pool can I combine these two data sets? The more data you can combine, the more precise your model parameter estimates will be. But if they're fundamentally different across your observational windows, then you can't combine them. Then you really need to explicitly model that, that my model on a Monday at noon operates differently than my model at a Tuesday at 8 a.m. So you might need a different arrival rate per hour of the day. You might need a different arrival rate per day. You might need a combination of those. Or you might find out that as long as it's a weekday, 8 a.m. arrivals are exactly the same. So sometimes what that requires doing is fitting models on a small set of data on Monday and another small set of data on Tuesday, and doing like a 2-sample t-test, seeing if you notice any differences from Monday to Tuesday. If there's no differences at 8 a.m. from Monday to Tuesday, you can then make the argument that you can combine 8 a.m. across Monday and Tuesday so you can get more data to make a better model. So so homogeneity versus heterogeneity. So there's a question here. Can I more explain what I mean by homogeneity versus, so a homogeneous distribution of statistics basically means that the statistics are the same across our observational windows. So Monday at 8 a.m. and Tuesday at 8 a.m., if people arrive statistically in an equivalent way, then I say that it's kind of like, well, those data sets, it's kind of homogeneous. I can just pull that together and just call it 8 a.m. I don't care about the day. The day has no effect. But there's heterogeneity across the day. So 8 a.m. is going to be very different than noon, is going to be very different than 4. So I don't want to just make a Monday arrival rate, because the arrival rate varies across Monday. So we wouldn't just have a single exponential distribution for Monday inter-arrival times. We'd probably have an exponential distribution for 8 a.m., 9 a.m., 10 a.m., 11 a.m., and so on. Maybe we might need, for 8 hours of the day, we might need 8 exponentials. And that would be a heterogeneous distribution, is what I'm kind of saying there, is that it might always be exponential, but the rates you use are heterogeneous. They vary. So there's a mixture of them throughout the day. Does that make sense? All right, and then I already kind of gave this example for data censoring, is that, for things that are over long time windows, you may not observe them for long time windows. Pharmaceutical trials, this is a big one. You say there's no side effects because we observed for 6 months and the patient or the participant in the study did not show any side effects. And then they show a side effect at month 7. And so how do you deal with that? So failure time distribution is the same thing. So you have to be careful about this. And censoring can work the other way too, is that you might have 1,000 light bulbs and you don't ever observe long failure times for the ones that fail outside of your observation window. And so you might just remove those light bulbs from your data set and say, these are the failures that we noticed. And you notice all of your failure times are going to be less than your observation window because that's the only time that you had there. So you will then make it, your model will then have failures that happen far too rapidly. So there's a lot of effects of censoring your data, of getting rid of data that's outside of your view. And you have to sort of try to figure out how to deal with that. And there are statistical methods that help you deal with that. And then there are kind of more back of the envelope ways to deal with that as well. But you need at least to be aware that that what you're doing might not actually match reality because you can't watch something forever. So hopefully that word censoring makes sense to you. Accidentally kind of removing data. And the other thing that I want you to point out that you will be able to see in your data sets is that sometimes there are relationships between your data sets. And so there's going to be an ICA where we talk about this as well, where there's a scatter plot of inter-arrival time versus service time. Now, these two scatter plots, what I've done is I've just sorted the data in a different way so that this is what I call a marginal distribution. So these are the inter-arrival times alone. I've marginalized them. I've pushed them all down and just said I've gotten rid of service time and only looked at inter-arrival times. So each one of these dots is an individual customer. And this is the time that took for that customer to arrive. And this is the time that took that customer to be served. And here, and if I can marginalize the service time, I can push everything down to the service time, so I only look at that. For these two settings on the left and on the right, the marginals are the same. But on the right-hand side, there's correlation between those. And so these two variables, these two random variables are correlated. And I would only notice that correlation by putting up a scatter plot and asking, is there some predictability I get by knowing one variable to predict the other variable? And so that's really important because you'll get a totally different system if there's correlations here. And so we've, you know, say, how do you generate these correlations in a simulation? If you look in the advanced section of lecture E2, which I didn't cover, but I've got slides on it, there's something called NORTA, which is normal to anything, which is kind of the standard way of generating correlations between random variables if you have to do it by hand. But also in ARENA, there are simpler ways to do that. So if I have an inter-arrival time distribution and I look back at my graph here, I can fit a line through this graph, like a regression line, and I might be able to then build a simple model which sort of uses the slope of that line and an inter-arrival time, which is drawn randomly, and I add a little bit of noise around that. And this can be my expression for service time distribution. So rather than drawing a fresh service time distribution, I base my service time on my inter-arrival time and then add a little bit of noise to fuzz that around. So that is something we can do when we notice that there are correlations in the real data set that we want to add to our simulated data set. All right, and then autocorrelation. So if you've, sometimes you're gonna notice data that looks like this one here, where instead of being, so this is, let's say these are service times, and if they're independent, then one customer's service time does not predict the next customer's service time. But you might be in a situation where service times somehow predict the next service time. So for some reason, people who need a particular type of service only come at a particular time of day, and they kind of come in waves. And so if you notice this kind of these kind of periodicity here, then there are things like autocorrelation, which we'll learn more about now that we're post-midterm. There are tools in ARENA that can analyze autocorrelation that can show you that, you know, actually I need to add a little bit of periodicity to my data so things go up and then come back down. And so I've just kind of given some examples that this is kind of more advanced, but if you're interested in how you might implement something like that in ARENA, here's some expressions for how you might do that. And we can talk about that if you actually need that for your systems. All right, so the last thing I want to just mention here, as I already talked about, is just knowing the difference between inputs and outputs. And so I've tried to beat you over the head with this pre-midterm, is that there are certain things that are output variables and there's certain things that are input variables. So inter-arrival times and service times at the fine-grained level, those are inputs to your system, but waiting times are outputs to the system. So we're going to do input modeling to choose probability models for these input data, but then we'll later do output validation. So the distributions of things that come out of our model, we'll then compare those to the distributions that come out of the real world. And if those distributions match, then we know we built a model that's a good proxy for the real world. But that's separate. So we do care about the distribution of what comes out of your model, but those aren't what we mean by input models. So you should still gather data on output variables because you're going to use them for validation later. But that sits, you put that on the side because you're not actually going to model. You're not going to fit a curve to that and then implement the curve. You're instead going to build a model, and then the distribution that comes out of your model, you'll then pick that data back up and compare. And that's what we do in the validation step. And we've got a whole unit based on validation. So that's kind of like what I want to cover today, these basics of collecting data. And then we're going to make this a little more rigorous in next lecture, where we say, all right, I've collected my data. How do I build a probability distribution? And how do I do these structural changes that I talked about, like dealing with bimodal distributions and trimodal distributions? So we'll do a nice example of that starting in the next lecture. And then PP plots and QQ plots, which some of you have probably seen before, we'll revisit those. Then after that, we'll talk about how to actually fit the parameters to these things. And then finally, we get to go and modify the chi-squared and KS tests to be far more general and allow us to test these different distributions. All right, so any questions? That's kind of all I've got for you, but we'll do an attendance question here. So maybe I'll put the attendance question slide up here, and then I'll be happy to take any questions as we do that. So the attendance question, I'll just put the link in the chat. And the attendance question here for you today is, let me think. You could say, give an example of an output variable that we would measure for validation, but not for input modeling. So that question is in the chat there. So I just mentioned a couple of examples. So give an example of something that we would measure to make sure our model, our simulation is running correctly, but we would not fit a distribution to it and use it as an input model. And so with that, are there any questions that I can address? Otherwise, that's all the content that I have for today. So if you don't have any questions, you don't have to hang around. But if you have some questions, I can hang around for a couple of minutes. And thanks again for your patience with poor Fritz. All right, just a reminder, Tuesday is kind of another midterm review for those of you who want another shot at discussing the midterm. For those that want to take the retake, it'll be a week from today, Thursday. No class that day on that Thursday. It'll be set up just like the first midterm, so it'll be available online. And I'll make sure that you have the ability to see your incorrect answers. So I'll get that fixed sometime, hopefully today. All right. Okay, doesn't look like we've got any questions. So I will go ahead and end the meeting and see everybody, if not Tuesday, then the Tuesday after that for the next, for lecture G2. And so good luck on your retakes if you're deciding to take them. And have a good weekend.